Even though this looks like 3 long, complicated topics in today's lesson, the notes really are not all that long. And so do not panic. It is actually a relatively easy lesson for us to work through. When we are doing some functions that are trig functions, we sometimes have to make sure that we check our final answers to make sure that they really work in the original problem. We know that about other kinds of problems. We know that if we have log equations, we have to check that we only have positive arguments, right? And if we have a value for x that doesn't give us a positive argument, we have to throw that away. Do you remember some other kinds of problems where it's important to check that your answers really work in the original equation? Gave you a little bit of a hint in the name of the lesson. What other kinds of equations do we have to check? Mia. Radical equations. So if we have a square root in the equation, we already know we have to check, do our answers make sense? So what if it is a trig equation? If it's a square root equation, we still have to check, do the answers make sense? Do they really work? So this one is kind of duh. We still have to do that no matter what. The other one that we're going to have to check for will be if we have more than one factor in there, so that we're getting solutions from one factor and solutions from another factor. If we have any tangents, cotangents, secants, or cosecants in there, we have to check and make sure that whatever we got from one factor really is still defined in that factor that had one of these other 4 in there. Because tangent is undefined, 90 and 270 degrees, cotangent's undefined, 0 and 180 degrees. Secant is 1 over cosine, so it's going to be undefined wherever cosine is 0. So let's run through some examples of how this works and what we're checking for. So it's got trig in it, and it's got square root things in it. What do you think you need to do first when you have any kind of a square root function? What's the first thing you do? Hope? Not yet. Well, if I had, I don't know, 5 minus the square root of x plus 9 equals something, what would you do first? What would you do first on that one? So we're going to isolate the square root first. So let's see. I would kind of like to get rid of that minus sign too. So let's pull that over on the right side. And let's say that the sine of x is equal to the square root of 1 minus sine squared x. So once you've isolated a square root, what have you done in previous problems, Skylar? Square both sides. And if we do that, it's not the sine of x squared, but the left is sine x times sine x, or sine squared of x. And over on the right, square gets rid of the square root, so we have 1 minus sine squared x. Now somebody give me a good idea of what we ought to do with this one. Somebody who hasn't already answered. Yeah, let's get those like terms together. Let's add sine squared to the other side. So now I have 2. Sine squared of x is 1. What next? Morgan. Divide each side by 2. And then that means that the sine squared of x has to be a half. And when you have something squared, what do we do now? What do we need to do now, Jen? And whenever we square root both sides, we have to remember plus or minus square root. So we are looking at the sine of x is the positive or negative square root of a half, but that's plus or minus square root of 1 over plus or minus root 2. And if we rationalize the denominator, plus or minus root 2 over 2. Does that look familiar from our unit circles? Okay, let's do these separately because that will make it easier when we are plugging things in. I want to know where on the unit circle is the sign positive root 2 over 2, and where on the unit circle is the sign negative root 2 over 2. So help me out here. Maya, where is the sign positive root 2 over 2? 45. Perfect. So x is 45 and 135 degrees. This one did indeed have the restriction that it had to be degrees, not radians. What about negative root 2 over 2? Where is that going to happen? Shane. Perfect. 225 and 315 degrees. Now, because this was a radical equation, we need to go back to the original and check that these values actually work in the original problem. So we are going to go back to our original sine of x, minus the square root there equals 0. So we're going to plug in if x is 45 degrees, these will be our checks. We have the sine of 45 degrees minus root of 1 minus sine squared 45 degrees. And we want to figure out if that's going to be equal to 0. Well, for 45 degrees, we know that the sine right here is root 2 over 2 minus the square root of 1 minus. And if we take root 2 over 2, the sine of that, and square it, we have a half. So we have root 2 over 2 minus the square root of a half, which is root 2 over 2. So that gives us 0. So 45 degrees was great. Everybody follow that check, okay? Okay. Now, since 135 came from the same factor, what would happen if we did 135 degrees? So if I change sine of 45 to 135 degrees in both places, I'll still have positive root 2 over 2 here. I'll still have positive root 2 over 2, square that and have a half, so this work will be exactly the same. So that one also works. Now let's see what happens if we check the ones that came from the sign being negative root 2 over 2. So if x is 225 degrees, then I have the sine of 225 degrees minus the square root of 1 minus the sine squared of 225 degrees, which means I have negative root 2 over 2 minus the square root of 1 minus negative root 2 over 2 squared. Well, that's still going to give me a half right here, so I'm still going to be taking minus the square root of a half, but I've got a negative out here in front. Is that going to give me 0? Are those two going to cancel out? So that one does not work, so we have to get rid of 225. And what if I change it to 315? If this is now 315 degrees and so is this, do I still get a negative root 2 over 2 here? Do I still have this very same work here? So that one also does not work. So the two that we keep are 45 degrees and 135 degrees. That makes sense to everybody? Hope. You need to think through all of them. You might be doing, a cross through like I did on that to be efficient. It's going to be the same work. All right, let's try the other kind of problem. So said these would be equations that have more than one trig factor. Nice that they've already factored this one for us today. So this part is very easy to get started and say that the tangent could be the square root of 3, and the sine could be negative 1. Question? For this still, yeah, it's still trig. And we've had ones on last night's homework that were very similar to this. They just haven't given us any where we get x equals something that causes a problem. They've been very careful in the problem sets up to now that when you have ones where you had to do the factoring and end up with something like this maybe, that you weren't going to get any problematic answers. Today we're getting problematic answers. So where on the unit circle will the tangent be positive root 3? And this one is in radians. Ian. Yes, but radians. A hard kind. What? Yep. Yep, so he did the hard part. X is pi over 3 in the first quadrant. What's the third quadrant one going to be? In radians. Morgan? 4 pi over 3. 4/3 pi. Everybody okay with those now? Okay, easier one, hopefully. Ariel and radians. Where is the sign -1? There we go. So now we just have to check. What we're checking for in this case is, are both factors defined for all three of those values? So if I plug pi over 3 into the first factor, so I'll write these out once here. So I'm going to plug back in here and check. We're going to see what happens. So if x is pi over 3, the tangent is root 3. So this factor becomes 0. Extra parentheses in there. And then I would have times sine of pi over 3. Is that some? So sine of pi over 3. Is that defined? Root 3 over 2? And is that something I can add 1 to? So that's a number. So 0 times a number is 0, so that works. If I try 4 pi over 3, I get root 3 for the tangent of x. So I've got 0 again. And for 4 pi over 3, I have minus root 3 over 2. Can I add 1 to that? Get a number? Times 0, I've got 0. So both of these work just fine. And that's to be expected because sine and cosine are defined for every angle we can come up with on the unit circle. But the problem comes because tangent is sometimes undefined. So we need to make sure 3 pi over 2 makes sense if we plug it in here in this original equation when we have tangent. So if we put 3 pi over 2 in on this second factor, no problem. We have -1 plus 1. That's 0. But if we try to put tangent of 3 pi over 2 minus root 3, what's tangent of 3 pi over 2? Undefined. So if it's undefined, can you subtract your root 3 from an undefined? And can you multiply an undefined by something? So that one is not going to work, so we have to get rid of that one. Questions? All right, let's talk about our graphs of log functions next. So if we want to graph y equals log base 4 of x, y equals log base 2 of x, y equals log base 7 of x, you're going to start seeing a bunch of these in your problem sets. First thing that we want to do is to change y equals log base 4 of x to its exponential form. So exponentiate both sides, and what do we have? Tessa, what would be the exponential form of that? So 4 to the y equals x, or x equals 4 to the y. These are the same thing, just in two different forms. Then I want to think about the inverse of that. Now for inverses, we just switch x and y, right? So the inverse would be y equals 4 to the x. And we know how to graph that. I can do a table of values for this inverse. If x is 0, what's y? If x is 1, what's y? If x is 1, what is y? 4. If x is 2, what is y? I can plot those points. This is the inverse. It's not what I'm really asked to graph, so I'm just going to do dots. 0, 1, 1, 4, and then 2, 16 is up here off the grid. And so I have done enough exponential graphs that I could plot that one. Now I want to go back to what I'm really supposed to graph. So I want to go from y equals 4 to the x back to x equals 4 to the y. So I just need to switch my x and y again to go back to my original one. So for my real function, that doesn't want to cooperate, we'll just do it that way. For my real function, I am going to switch the x and the y, which means I can switch all of these x, y coordinates. And for my real function, I need to include 1, 0, 4, 1, 16, 2 until I'm off the grid. So 1, 0, and 4, 1, 16, 2 is going to be way off there somewhere, and draw in my graph. And every log graph will have that basic shape. If it is y equals log base b of x, it will go through 1, 0, and label that one 4, 1. It will also go through whatever the base is, comma 1. So if we have a small base, like 2, we might have 3 or 4 lattice points we could plot on our graph. But if we have, if the base is 5 or 7, we're only going to have those 2 lattice points before we're off the grid. Does anybody have questions on that? Because that's it for our notes for today. So you agree with me, it was not as